All right, so chapter 19 is about thermodynamics. All right, and this is something that would have been discussed a little bit in the first semester of the course, and now we're going to build off of that. Okay, so let's kind of just review here. One of the first things that you would have talked about with regard to thermodynamics is what's called the first law. The first law of thermodynamics, this is a very important principle in all of sciences, and that is the idea that energy cannot be created or destroyed, only transferred. All right, so you're never creating new energy, you're never destroying any energy, you're just transferring it, okay? If we think about, obviously we got energy powering the lights in this building, right? It's not like that energy just came out of nowhere. Mostly it was generated by breaking existing hydrocarbon bonds and transferring that energy into useful energy, into work. Your car, for example, if you have an internal combustion engine, it's taking that gasoline and transferring the energy in those bonds into then the motion of your vehicle, right? It's not creating any energy. Energy is not being destroyed. It's just being converted from one form to another, all right? That's part of what makes energy kind of a pain in the ass, is that it shows up like all over the place, right? We talk about bond energy. We talk about potential energy in physics, right? By raising my phone above the ground, I've been giving it potential energy that will be transferred into motion when I drop it. We're going to talk about entropy, which is a weird form of energy. Energy kind of shows up in a variety of ways, okay? It's because it's not being created or destroyed, it's being transferred from, for example, bonds into motion. All right, but that's our first law of thermodynamics. We can't make energy out of nothing. Energy is not going to be destroyed. It can only be transferred. What we're going to talk, and we'll formalize this a little bit as well, but we'll talk about the second law of thermodynamics. All right, and we'll sort of formalize this here in a bit after we introduce this concept of energy. But to just kind of set it up, the bottom line of the second law of thermodynamics is that the universe hates concentrated energy. The universe is constantly spreading energy out, spreading energy throughout the universe. It hates when energy is in this nice concentrated little form, okay? So there's this universal push, this drive to spread energy out. It's going to happen way, way after we're gone, but there will be a point far in the future where every inch of this universe has the same energy level. All the stars will be gone, all the planets will be gone, everything will be equally distributed throughout, okay? Stars have finite amount of lifespans. They're constantly going through this process of releasing energy, and finally they die to the point where all of that energy that was once concentrated is spread out throughout. I'm going to be dead honest, I know nothing about space, all right? I know that this principle very much so applies. Space is very much so not my forte. But nonetheless, there's this universal push towards spreading out all of the energy that's been concentrated in the universe so that eventually it's all going to be evenly distributed. And this kind of fundamental theory underlies all of what we're going to study with regard to thermodynamics. The other thing that we want to keep in mind that kind of will help us out is we want to think of the universe is the energy tax man. Nothing happens in the universe without it getting a little bit of cut of the energy that's being distributed. Okay? Even things that aren't terribly favorable, the universe is always getting its cut. Nothing happens without the universe getting a cut of that energy. And what the heck do we mean by that? We'll sort of formalize this here in a bit, okay? These are just two kind of simple concepts to keep in mind as we're going forward. The other thing to review that we've talked about before is the idea of enthalpy. All right, this is something that you would have talked about previously. So, one of our goals for today is going to be to construct a concept of what we call a chemical potential. All right, we want this formula for a chemical potential. That's going to be our goal for today. All right, and what do we mean by chemical potential? This will be a value that tells us whether or not a chemical process occurs. All right, so is there a value for a chemical reaction that we can calculate that will say whether or not this chemical reaction will actually occur? All right, that's our goal for today. And sort of a natural starting point for our chemical potential is going to be an energy quantity that we know is very important to chemistry, and that is delta H, or enthalpy. All right, and what we're going to see is that this enthalpy is going to be a really important term in our chemical potential, but there's something missing here. And we'll try to figure out what that is. Okay, so our chemical potential, whether or not a reaction occurs, it's going to account for the enthalpy of that reaction, but then there's this missing part here that we're going to fill in. But let's take a second and rewind and talk about enthalpy. All right, let's remember what enthalpy is. Does anybody remember what enthalpy has to do with? What were you measuring when you were sort of talking about enthalpy? So energy for sure. It is a form of energy, right? But we're going to talk about a lot of different forms of energy. So specifically, which form of enthalpy of energy are we talking about with regard to enthalpy? Thermal energy, heat, right? Absolutely. So enthalpy is the exchange of thermal energy which we call heat. The vast majority of chemical reactions that happen spontaneously release heat when they do so. Okay? This is what we call exothermic reactions. Exothermic reactions have a negative delta H, meaning that they release heat, release thermal energy. All right, so again, if we're looking at this idea of a chemical potential, we want this value that tells us whether or not a reaction will occur. Well, we know that reactions that happen spontaneously tend to release heat. So we're definitely going to have this enthalpy term in here, okay? The problem is that there do exist some reactions, and they're way less frequent or more rare, that actually absorb heat, okay? These are what we would call endothermic reactions. They have a positive delta H. All right, so again, all this, the big brain scientists actually at like a ridiculously early part of chemistry, like 1700s, they're coming up with this crap, right? Which is just amazing considering that they didn't even really have proof that atoms existed yet. All right, but anyway, big brains back in the day coming up with this concept. They want to develop a chemical potential to tell them whether or not a reaction is going to happen. They know that most reactions release this thermal energy, so that's a great place to start. But then they're kicking themselves because they got this small batch of examples that actually absorb thermal energy, that are endothermic, yet are still happening spontaneously, right? So let's just look at a very simple example of one thing that would be killing them, would be the idea that if I take ice, solid water, I stick it on the bench top and I let it melt into liquid water. Well, the only way that it's going to be doing this is if it's absorbing thermal energy, right? So melting of ice, going from solid to liquid water, this is an example of an endothermic reaction. But I think we're all well aware that ice will indeed spontaneously melt, right? That's not like breaking news. So how the heck do we account for this here? Okay, we have to introduce this new quantity, which we actually talked about a little bit before, but now we're going to really sort of formally introduce it, and that is entropy. Entropy, we have the symbol delta S for. All right, and we're gonna have this like simple way of thinking about entropy, and then we'll sort of give the formal definition here, but our simple way of thinking about it is gonna be by far the most useful, okay? So our simple way of thinking about entropy is that it's the energy of disorder. This universal push towards disorder. All right? And I remember being a student first learning about entropy and being like, what is that nonsense? First of all, energy of disorder, that is ridiculous. That does not sort of make any sense in terms of the world that I know. It's really hard to latch onto. And I was positive that I was going to get further on in my chemistry life, and I would realize that this is like this BS definition, and really it's got like something more important. Honestly, there is a formal definition of entropy. I still think about it this way. This is what entropy is. This is the way you want to think about entropy. The universe, for whatever reason, wants things disordered. There is a energy quantity dedicated towards pushing this universe to a more disordered state. Not something that you would know just walking around in your daily life, but turns out there is. All right? So this is our energy of disorder here, and this explains why water will spontaneously go from being a highly ordered solid state, right? If we think about ice, this is highly ordered, into the liquid phase, which is then more disordered. Again, this process is absorbing thermal energy to do it, but it's creating more disorder, which is why it is a spontaneous process. The universe will allow things to absorb thermal energy. They'll allow these things that are sort of from a thermal energy standpoint unfavorable. The universe will let it happen. It'll give it a pass as long as it creates disorder in the process, as long as it's more chaotic at the end of the day. All right? So this is our entropy, helps us explain why we go from this highly ordered state to a disordered state despite the fact that we're absorbing thermal energy in the process. All right. If we want to sort of be better and have this like formal definition here, entropy is the number of chemically equivalent microstates. All right. Entropy is really a measure of what are called microstates, the number of chemically equivalent ways to arrange a system. Systems that are highly disordered, you can sort of arrange things more way in order to create a disordered state, right? A good example of like the universe's push towards disorder, because again, I know that that's like a bizarre concept here, but let's think about something highly ordered like a house, right? If you're going to build a house, that is a huge, like a highly ordered structure that you're creating. You have to have the certain amount of boards, certain right length of boards, the cut has to be right, the nails have to be in a certain place, all that sort of jazz, right? So building a house is building this very highly ordered state. There's only a certain number of ways that you could sort of switch boards around or nails around in order to get the same structure, right? The universe comes along. We got these high, extreme weather events here. It's mostly fires that you're worried about, but like tornadoes and hurricanes and all that jazz. And what do those tend to do to those highly ordered structures? Turn them into a pile of disorder, right? I personally have never seen a tornado take a pile of boards and build a house out of it. It's the opposite, right? It takes this highly ordered structure and turns it into this pile of rubble, this disordered structure. Right? And there's a lot of ways that you could stack up those sticks and get that pile of rubble compared to your highly ordered state, your house, right? So the universe, if it gets its way, everything would be disordered. This is especially weird for us as humans because we are about the most highly ordered thing that you could possibly imagine in this universe. Life is absurdly entropically unfavorable, all right? It's like just bizarre that this much order exists. Our cells have just so much order involved in them. But the universe hates us, right? I mean, look at how many of us exist in the universe as a whole. I'm sure there's life out there, but at the very least, it is far away, right? We are few and far between out here in the universe. So having something like a life form, this highly ordered structure, is just very, very unfavorable. It doesn't happen very often. And look at how much work we got to do to keep us alive. We got to eat, we got to sleep, we got to be able to go to the bathroom. We got all these things that we have to do in order to keep this machine running, right? So bottom line is that order, not very favorable from the universe's standpoint. The universe likes to push things towards a disordered state. All right, so let's look at a few processes and see if we can't figure out which would be considered entropically favorable or unfavorable. Okay, and by entropically favorable, we mean creates more disorder. Entropically unfavorable is then the opposite, right? Something that would create more order. All right, so now let's think if we took liquid water and we stuck it in the freezer, would this be a process that is entropically favorable or unfavorable? Unfavorable. Now we're creating more order. And this is a spontaneous process as well. We'll talk a little bit more about this push and pull between entropy and enthalpy. All right, but now just thinking only of the entropy component here, this is indeed a process that is unfavorable. What if I took liquid water and I boiled it so that it went into the gas phase? This would be an example of an entropically favorable process. Okay? So, and this is by far kind of the most important if we're going to rank things that influence our entropy here. We'll do that at the bottom. The gas phase is by far the most disordered of all the phases compared to the liquid phase, which is fairly disordered, but things are still interacting pretty strongly. And then the solid phase is by far the most highly ordered of all the phases. Right? So any process that turns, for example, a liquid into a gas or a solid into a gas, that's even better. That would be an entropically favorable process, right? Because you're creating that more disordered gaseous state. All right. Okay. Now let's say that I take tetranitrogen dioxide, and this decomposes into two dinitrogen monoxides. Both of these are gaseous molecules, right? But would this be entropically favorable or unfavorable? Anybody got a guess? Favorable. Why favorable? Because you're creating more gas, exactly, right? So more particles is more disordered, absolutely. So again, solids more disordered than liquids, more disordered than, gases more disordered than liquids, more disordered than solids. Another big thing is more particles, the better. All right, what about if I went from sodium chloride in the solid phase, took it and dissolved it into solution to create an aqueous solution? So this is favorable, and honestly, this is a little bit more tricky than it appears. Yes, I mean, if you just think about it broadly, we're taking sodium chloride, they're bound together in this highly ordered lattice, we put it into water, all of a sudden those ions dissociate and they're freely floating around, right? So this would be an example of a favorable process. Okay, so we'll also add to our list creating a solution. But we are going to put a little bit of a star next to this because we'll see that this is actually a little bit more subtly complicated than we're talking about now. And so we'll sort of revisit this. For right now, we're going to say just flat out creating a solution, entropically favorable. And like in the next chapter, we'll show that maybe it's a little bit more complicated than this. All right, but for right now, creating a solution, yes, more favorable. Other things that might be more counterintuitive. Would be increasing the temperature. All right, so just in this room right now, if all of a sudden we cranked up the thermostat, we would actually be increasing the entropy in this room. Right, because temperature is closely tied to the kinetic energy of molecules, so things are just moving around faster, more disorder going on at higher temperatures. All right, and then the same thing is also true if you increase the volume. All right, this will also increase disorder just because there's more places for all those molecules to go. All right, so this is our sort of list of entropically favorable considerations here. All right, and then the last one, let's take a look at two different gaseous molecules here. Let's do... So now this is comparing carbon dioxide. I guess if I'm being good with my Lewis structure, I'll put in my lone pairs. All right, comparing carbon dioxide with C3H8, which is propane gas. Which one of these two molecules has more entropy, more disorder, just based on the structure? This is something that I don't think is kind of easy to guess, but if you actually build a model kit, you can convince yourself of this pretty easily. All right, more bonds to rotate equals more entropy. All right, if you build this model of carbon dioxide, it's kind of like a little bit of a brick. Those carbon-oxygen double bonds don't rotate. They're just kind of stuck in that same conformation. If you build a molecule of propane and you kind of whip it around, it'll sort of rotate about all these bonds, flail about, right? So larger molecules that have more bonds that they can rotate about, they're more disordered molecules. They can be in a variety of different, like, rotational states is what they're called. But bottom line is, more bonds that you have to rotate, the higher entropy that molecule is. Oops. All right, so let's just look at a few example reactions, and you guys are, again, going to, just given what we've talked about, things to consider, tell me whether these are entropically favorable or unfavorable. All right, so these are three chemical reactions, and we want to think of them from an entropy standpoint, whether or not they are entropically favorable or unfavorable. All right, so this first reaction here, let's take a poll here. Who thinks that this would be entropically favorable? And who thinks unfavorable? Yeah, so this would be favorable. Why? It's just a counting game, right? I got gases on both sides, but I'm converting what would be like 2 moles of gas into 5 moles of gas, right? So I'm just creating more gas molecules and thus more disorder. So yes, this would be favorable. This next reaction here would be what's called a precipitation reaction. I take these two aqueous solutions, I mix them together, and this solid precipitates out. Would that be entropically favorable or unfavorable? Yeah, this would be an example of an unfavorable reaction because my solutions are relatively disordered. And then I'm creating this highly ordered solid. So this would be an example of a reaction that is entropically unfavorable. All right, and then the last one, I have this solution. Carbonic acid turns out to be unstable. It's going to decompose into carbon dioxide and water. Is this favorable or unfavorable? This is favorable, whoops, because we're creating a gas. Any reaction that creates gases are, from the entropy standpoint, favorable reactions, right? Creating more disorder by creating that gas phase. All right, so now we're going to go back and we're going to formalize that second law of thermodynamics, right? We kind of had this things to keep in mind. Now we're going to do like the textbook definition of the second law of thermodynamics. All right, and simply put, the second law of thermodynamics is that the change in entropy of the universe has to be positive. Nothing occurs unless the change in entropy from the universe's standpoint is positive. So we can sort of, what the heck is this line of math saying? All spontaneous processes increase the entropy of the universe. All right, so let's think about this entropically unfavorable process. An example that we talked about before would be if we take water and we freeze it. All right, so this process is entropically unfavorable. So how does it occur spontaneous? How does it occur spontaneously, rather? It's a transfer of energy. So yeah, you're close. So what we're going to do is what scientists do is they break things up. They take the universe as a whole and they break it up into two parts. The system and then everything else, the surroundings. All right, so we're going to take our universe and we're going to break it into two parts. Our system, all right, and in this example, our system is this water freezing. But then the other portion, in order to make up the entire universe, yeah, I have that water that's doing its freezing, but I then have everything else, the surroundings. Okay? So again, this process cannot occur unless the universe is increasing in entropy. But as we said, this is a entropically unfavorable process here, right? So that means that the system has a negative entropy. So then how is it going to work out here that my universe ends up being positive? What's going to have to happen to my surrounding entropy? It's going to have to be a positive, and in fact be a large positive number, right? As long as my surroundings are increasing in entropy, then this entropically unfavorable process will be allowed to happen. We can freeze ice as long as the entropy of everything else is increasing. All right? And so how does that happen? Remember, we said that increasing temperature will increase disorder. Is this right here an endothermic or an exothermic process? Is it going to absorb energy, thermal energy, or is it going to release thermal energy in order to become a solid? This is an exothermic process. So this explains why this is allowed to happen, because this process releases heat to the surroundings, right? That release of heat increases the entropy. So it turns out that when you put a tray of ice in the freezer, yes, the freezing of that ice cube is an entropically unfavorable process. The universe lets it happen because those water molecules release thermal energy into the rest of the freezer. So the rest of the freezer is in a more disordered state after that ice freezes. Okay? So our delta S of our surroundings is going to be proportional to what happens to the delta H of our system. Again, if our system releases thermal energy, that increases the entropy of our surroundings. All right, and Long story short, a lot of experimentation determined that it was proportional inversely to the temperature as well. So my delta my delta S of my surroundings is just equal to the delta H of my system divided by the temperature. So as long as that system is releasing thermal energy, makes it entropically favorable. Okay? The only thing is that because of our convention here, remember that we say exothermic is negative, and we want entropy for it to be favorable as positive. So we're going to throw a negative sign there as well. All right, so again, an exothermic reaction, something that releases heat, has a negative delta H. That's good for the surroundings. That will increase the entropy of those surroundings. All right. Now, what we really want to be able to do is to define everything in terms of the system. So we're going to take this equation here. Delta S of the universe equals delta S of the system plus the delta S of the surroundings. And we're going to plug in what we just found out about our delta S of the surroundings. The fact that this is just equal to negative delta H of the system divided by temperature. All right. So entropy, the units are joules per Kelvin. And we want to take this equation and redefine it in terms of just energy. So what we're going to do is just multiply everything by negative delta T, or negative T. This just puts each of those terms in units of joules instead of joules per Kelvin. So we have negative T delta S of the universe equals negative T delta S of the system plus delta H of the system. All right, and then according to our second law of thermodynamics, nothing's going to happen unless delta S of the universe is greater than 0. So that means negative T delta S of the universe is what? Greater than 0 or less than 0? If delta S of the universe is positive, then what about negative T delta S? Is that going to be positive or negative? Negative. All right, and so believe it or not, now we have built our chemical potential here. We're going to call this guy T delta S of the universe, the thing that has to be negative, or negative T delta S of the universe, the thing that has to be negative for this process to be spontaneous. We're going to call this delta G. Delta G equals delta H minus T delta S. This is our chemical potential. Delta G must be negative for a process to be spontaneous. All right, because if delta G is negative, that means that the delta S of the universe is positive, and that was our condition for things being spontaneous, right? So our whole goal was to build this chemical potential here, this formula that would allow us to predict whether or not a reaction or any chemical process occurs spontaneously. We sort of hinted that it was going to have this enthalpy component here, whether or not that process absorbs or releases heat. But that's not the whole story. You also got to account for the entropy of that process as well. Some things can be some things can be endothermic as long as they are entropically favorable, as long as that other component is favorable. All right? And so this is kind of what the bulk of this chapter is going to revolve around, is this formula right here, using this formula to help us talk about chemical reactions.